Welcome. My name is Peter Bøgel, and I'm a professor at the physics department at the DTU, Technical University of Denmark. And together with Cedric Huyghebaert, also professor, we are organizing this. So we have been working on a real conference, CARBONLINEHAGEN, since 2010, and we had the last run last year. Maybe we did the same thing too many times, I don't know, but it went well and everything was fine. So we kind of wanted to stop it while it was good. And we didn't have any specific plans to sort of, plans of what to do. But then this sad and unfortunate situation happened early this year that threw us out of our normally routines. That means that a lot of scientists were sent home, and unless you're a theorist, it's a pretty devastating thing that you cannot go to the lab. And also everybody in science needs to interact, collaborate, and talk, because that's how science happens. But scientists are a bunch of people who are not easily stopped. So we can see many other institutions and universities are trying to sort of get everything going online, teaching, meetings, things like that. Very quickly, everybody was able to use Zoom and so on. So we also started to invite speakers online for our courses and so on. And we thought, why not share? It's so easy to invite more people in. And then we decided, why don't we relaunch CARBONLINEHAGEN, at least in the lockdown period, as this CARBONLINEHAGEN 2020. We haven't made a decision on how long we're going to do this. This is the first time we try it. And I can say personally, it's pretty scary for me to make a meeting with so many participants. So far, it looks like the technology is working. We have, in principle, room for 500, but let's see how it goes. For sure, if this turns out to be a success, we don't see a point in not doing it, even when things go back to normal, because it's hard to find any sort of meeting that is, compared to a normal conference. It's very cost neutral, very time effective, CO2 neutral, and it's available for researchers who do not have resources to go to as many meetings as they would like to. So there are lots of reasons why something like this could be nice. We don't have the possibility to shake hands and meet physically, but I would be very happy if you would care to answer a brief evaluation that I will send out, because we will need to learn how to do this well, because we think that this might play a role in the after Corona society we have, and that the scientific society could benefit for this sort of online gatherings. So today we are extremely honored to have Cedric Huyghebaert from Imec. Imec is a famous research and technology institution in Belgium, and he is currently a program manager of exploratory modules at Imec, and also primary investigator for Imec in the graphene flagship, and the deputy leader of wafer scale integration. And personally, I can say that since the first time I realized how far they were already years back, how much they already had done and had thought about that we were just starting to do. I think there's no better person to introduce to the progress, but also the challenges involved in large-scale integration of graphene, which is, of course, what many people are waiting for. Because how can we really push graphene from the labs and the imaginative experiments into products if we can't integrate it in the most successful technology we have? So I should also advertise before we start, give the word to Cedric, I should always also advertise the talk by Frank Coppens. I'm sure many of you noticed that we have another famous person coming and giving his unique perspective on quantum nano optoelectronics for 2D materials. And without saying too much, I can say that Frank will show us some stuff that has been shown for pretty much the first time. And I think it's very on the cusp of something that is going to happen. I'm very excited about this. So I suggest that if you didn't sign up already, that you have a look at the abstract and check it out. We also have other speakers lined up. Sarah Hay, Professor Sarah Hay from University of Manchester in the UK, has also kindly volunteered to help us out here, to help the scientific community keep the wheels rolling. We will announce the abstract soon, and we have more speakers coming up. But everything will be visible on the homepage that you already saw, and also I will make some announcement here and there as we get there. So I think I said enough. I'm very glad that you could all make it, and let's give the word to Cedric. Cedric, can you grab the screen, baby? And
yeah.
if you share your screen.
Screen, start with this one. Okay. Does everybody see my screen?
Yep, I think.
Yep. Okay. Hopefully this will work. So first of all, I would like to thank you, Peter, for giving me the opportunity to start in this new configuration. For me, it's also new. So I hope I will do a good job. I will do my best. And basically, well, it started 2 weeks ago or 3 weeks ago as an invitation to give an overview of what Imec was doing to the team of Peter, but it grew to a more larger platform. So I want to say good afternoon, but I even don't know if it's good afternoon for everybody. Maybe people are also in the morning or in the evening or in the night. So what I would like to drive you through is well, given a little bit an overview of the how we tackle 2D material integration in a 300 millimeter silicon pilot line, well, which are mainly the challenges and how we try to tackle them. For people who have seen presentations from me, some of the things will be known, but I try to give it a little bit in a new flow. So what is Imec? Well, Imec is a research institute that is in Belgium, situated in Leuven. And basically we have a relatively good infrastructure. So we have a 200 millimeter pilot line. We have some labs, solar cell, human brain labs, and then our jewel is the 300 millimeter pilot line that is relatively state of the art with UV lithography and so on. And well, we try to work together with partners to basically look for options for the industry on how to tackle and continue Moore's law, but also how to bring in new functionalities and new applications to that well wonderful tool, which is semiconductor processing, which started mainly for CMOS logic, but today is used for more and more application. And we have typically partners in the application space. We have partners in, well, we have fabless and fablite partners, IDM and suppliers. Well, this is a kind of, well, it's not a full overview, but just to tell you that we have a lot of partners, and then for 2D material, we have a lot of people that are also looking into what we are doing there, and together with us, they are thinking and looking to our results and see how they, if it makes sense, and how they can eventually bring that to their future products in later on. So what is Imec typically doing? Well, you have, I think, the academic world, which is bringing brilliant ideas, novelties, understanding, but typically at a level which is what we call the lab level. It's very important that these things are happening, but at some point in time, it's important to mature some of these ideas, to try to look what is really working, what is not working. Is it a complete offering? Can we bring it to a complete offering or not? And well, we also have labs, and we are typically incubating and looking and trying to play with these new materials first in a lab phase, and then already in the lab phase, we are preparing to upscale to, let's say, the 300 millimeter infrastructure. And it's very important because some of the approaches that we do in the lab are not usable in 300. So we need to sometimes rethink already concepts and so on. And basically, this is a typical, very complex exercise because there is always a little bit of gap between the academic world and the industry. And that's exactly where we try to position us. So being partners together with the academic world and the industry to try to to bring some of these concepts and ideas and hang that over to processes that can be used in the line. And then, well, I just want to mention this also that a lot of pilot line processes are offered to the academic world so that they can even later on, once the processes have matured and have been demonstrated in 300 millimeter, that they can still access making designs and demonstrate products that based on concepts that have been demonstrated in the lab, but that have been matured to the 300 millimeter processing. This is typically something that is done together with the European Union. I'm happy to say that for 2D materials, we will normally in October, we will start a novel initiative to try to mature these processes and really have stable processes in a 300 millimeter infrastructure. Application fields, well, in September this year, together with academics, together with people from the industry and ourselves, we made a kind of forecast about what could be done with 2D materials co-integrated on silicon, and we defined some application fields and also try to evaluate the potential markets. And well, this is a kind of motivation from why we should do this kind of integration and why there is a lot of potential for 2D materials. And to just show you that this is not science fiction, so we are saying that there is already a start of emerging market for sensors, and well, I will go through a few of them. Well, this is today, Graphenea is already offering a kind of sensor platform. It's a simple integration, but it is on the market and people can buy it. Towards 2D material sensors integrated on CMOS, well, ICFO has demonstrated very mature processing, and well, this is kind of promising, and they are using technologies that could be upscalable. So this could come to the market, and Emberion on the other side is already bringing linear arrays for infrared detectors on the market too. So these markets are starting to emerge and are starting to become reality, and this is all based on 2D materials integrated on top of CMOS well, logic.
Cedric, can I make a short comment? Just a message to everybody that Stephen Brems, Cedric's colleague, has kindly offered to try to answer chat questions that appears during Cedric's talk. So if you go to the chat window and ask something you are confused about or would like to know about, Stephen and others may try. You can also welcome to answer each other's questions if you feel you have the answer. So that's all. Thank you.
Just to continue towards optical interconnects, this is a kind of vision that we have, but we are also working, and basically we are integrated that already on 300 millimeter, is to make graphene-based modulators and graphene-based detectors integrated in a CMOS flow, and you can immediately see that we did that towards a Damascene module. So this has nothing to do with the lift-off processes that are typically from the lab. And well, we are still fine-tuning. We are not fully there, but this is the vision on how you could in a simple layer integrate active components on passive waveguides. Another field that is kind of emerging is the field of memory application, and I just took one out here. It's like resistive switching devices based on multi-layer hexagonal boron nitride. This was done in the group of Mario Lanza. And it's a very stable and reproducible process, and it solves some of the problems that you have with three-dimensional resistive materials. We also, and this could be even emerging slightly earlier than foreseen, but combination of graphene with interconnect metals seem to have some promise towards improvement of the resistance of the wires. And this is an exercise that was done at Imec by Swati, where you can see that by combining ruthenium with graphene, you have basically a lowering of 15% of the resistance of your ruthenium wires compared to without graphene. There are also like multi-layer interconnects, and we also did some work at Imec in trying to find out if there is a way to be competitive or even better to outperform copper. Next possible application, and this is definitely something that is very interesting, is like bringing in functionality in the back end of line. For example, you could make a transistor, and this is kind of an image of a transistor that we made, again with Damascene contacts and so on. So this is about 200 nanometer, the gate length, but bringing that inside the back end of line to switch off parts of the circuit eventually to for power management or for heat management, so that you can locally make your circuitry smarter and improve the functionality and basically the power management in your system. Or there are other possibilities like a memory selector and so on. So, but finally, the real goal of, well, the holy grail of 2D material integration is basically the replacement of silicon for CMOS application. And this is a very challenging one, but why 2D materials are so interesting? Well, if you want to scale your gate length to very short, to very short lengths, you need to scale the body of your semiconductor too. And basically what you see here is that if you do that for silicon or germanium, you see a dramatic drop if you thin down that body thickness. And 2D materials have the promise that, well, even for a monolayer, they could still have, let's say, relatively high mobilities, what you need for your drive current. And this is the very attracting thing there. The other thing that is, well, that we need to take into account is, of course, if you make the gate length extremely narrow, is that we avoid source to drain tunneling. And this is done by going to relatively high effective masses. But there, the nice thing about 2D material is that you have a zoo of them, and so that you can really choose the one that is the most interesting to have, let's say, enough high effective mass, but still, let's say, that thinning behavior. And basically, well, to show the promise, it has been, there is a famous paper where they're using the 1 nanometer gate channel, where they're using a CNT to modulate basically a molybdenum disulfide transistor. There are some questions about the paper, but nevertheless, it has the merit to prove that you can modulate with a very narrow gate, and this is quite interesting. Of course, before we start to integrate, we want to understand which kind of device we would have to integrate at the end of the day. And therefore, we did some simulation work to try to understand which is the design, schematic design of our transistor and how we could make that. So do we have a single gate, or do we need to have a dual gate control? And basically also to benchmark that with silicon. So this is basically a prediction for N5 silicon FinFETs. And basically what we are looking to is energy delay. So it means how efficient is your transistor and how fast you can switch basically your design. And there we see that for a low power application, a tungsten disulfide dual gate FET could become competitive with a silicon FinFET of the 5 nanometer technology, which is not the competition, but at least it showed that there is some promise in there. For high power device, this is not the case. So if we go to a single sheet transistor, we cannot be competitive. But you can become competitive if you work with, let's say, multi-sheets transistors, where you would have, let's say, a 2D material gated, well, several 2D material on top of each other. And basically, this is what is drawn on this graph. So again, you see energy delay. And basically what is in there is some assumptions. So we assume that we have a contact resistance of 100 ohm. Some of these things are not fully realistic, but at least these are numbers that we need to reach to become competitive with N3 FinFET simulations. And then you see that the number of stack is between 2 and 8 sheets of 2D material on top of each other. And then, well, here the difference that you see between this bullet and these bullets is the fact that in this assumption, we assume that we can have 300 centimeters square per volt second mobility in the material, in the tungsten disulfide, 600 and 900. These are, well, we do not reach these values today, but at least it gives us that even with a relatively modest mobility, we could achieve and being competitive with these numbers. Then what we also try to look is to the impact of, let's say, non-idealities, and see, depending on the different transistor devices, so dual gate, with overlap, without overlap of the back gate towards the contacts and so on. Well, it's all written in this paper of Devin Verek, but we try to find out how these transistors are sensitive to non-idealities, like reduced Schottky barrier for the contact, the ideal transistor, or let's say an increased mobility. So this is the calibrated, this is the model of what we have today. So the performance that we have today on flake transistors. And then if you would increase the mobility to 300, for example, this is the impact that you can have, and so on. So based on that, we try to look if there is a window, and that's, well, we are convinced that there is a window there for materials to be competitive with silicon FinFETs or silicon nanosheets. And that is, of course, driving the science that we do at Imec. But there are also a lot of integration challenges. Well, and one of the first one is that 2D materials, well, this is very obvious, but they are extremely thin. So there is no bulk. So once you have touched the material or destroyed the material, there is no way to, let's say, heal it through an anneal or whatever, because you can have no epitaxial regrowth, and it's there is no margin to stop. So if you want to do an etch or whatever, or you want to touch the material, you always need to be very careful that you do not destroy the material. And this is new, because in silicon we very often, let's say, clean up the interface to prepare a better interface by a pre-sputter clean or whatever, but this is all impossible to achieve. So the other thing is that these materials, if you let them to the air, or you're depositing in an oxidizing ambient, they are very prone to oxidation and surface damage sensitive. So adhesion will also be a very big challenge, and we are suffering from that problem all the time. A 2D a single layer 2D is very soft and bendable, and this will also be a very big challenge, because the material performance will also be dependent on the, let's say, the the control and the strain variation that you put in the material. If you increase the number of layers, we see that the rigidity of the stack very fastly increase, and this is maybe something that we will need to consider later on. And the other thing is that it's self-passivated material, so the growth, the nucleation of chemical vapor deposition, or ALD, is also very challenging and very irregular. And what we also see is that the temperature budget and the way they are expanding compared to the others, given that it's van der Waals bond, it's also a challenging thing in integration. So there are still some open question there, is how we will deal with that. Can we integrate a single sheet of material, or will we have to integrate multiple layers? And the other thing is, well, the next challenge is doing one single transistor existing out of one sheet, or doing multi-sheets. This is also a very challenging thing. The good thing is that, well, in literature, even today, we see that there is an increased performance of most of the devices based on flake transfer. So definitely there is an opportunity to reach these things, but how do we bring that to 300 millimeters? That's basically what's the topic about. We define basically 6 challenges. This is also in that Nature paper, where the decisions will need to be taken in order to mature faster and in a focused way on how we need to bring these materials to production. So, for example, for growth, we have different options. You can grow epitaxially eventually on a dedicated template, so van der Waals epitaxy, or you can try for a direct growth on an amorphous dielectric, for example. But the quality of the material will be maybe very different, and this will define where you can use that material or not. Or you can try to do area selective growth, so you have a controlled seed deposition, and then you grow a single crystal around that seed. This is not very mature, even in the lab. Not a lot of people have demonstrated that. Well, it is demonstrated for graphene, but for TMDCs, it's still very immature. Towards transfers, there is also quite some question. Do we need a transfer? Because if we go for direct growth, we can avoid the transfer. But nowadays, we see that we have a penalty, especially if we would like to do direct growth at low temperature. So there are also quite some questions. And then how do we transfer? Today in the lab, most of the people use wet transfers, but is that the right technology to upscale, or do we need to go to dry transfers? So a lot of questions still to be answered, and it's really the moment to try to enforce breakthroughs in order to have growth and transfer in place. Because later on, once these things are in place, we can go to the 300 millimeter fab, and we can really work better on interface, on doping, on contacting, because we have basically tools that are really designed for that are typically not available in the lab environments. So we need to really emphasize these 2 steps before we can go to the future ones. Of course, there are other challenges towards design and so on. So, well, now I will go to grow and well, discuss how we think we need to make step forwards towards the perfect crystal structure, because that's basically at the end of the day what we are after. So there are different techniques that you can use to do that. ALD has the advantage of being normally low temperature, and it's very established in the industry. But what we found out is that in the last 7-8 years, a lot of people tried it to grow 2D materials with ALD, but typically they did not succeed in really achieve high quality materials. To MBE, you have also a relatively large window, but this is typically not something that is really scalable to a high volume manufacturer, and also typically the good results needs to have the right templates. chalcogenidation, which is kind of an anneal in a chalcogenide environment. It gives relatively good quality materials, but typically we have small grains, and it's very difficult to tune the grain orientation. Well, at least we didn't find it out, and also in the literature there are not so many people that manage to have, let's say, opportunities towards a single crystalline grain. And then basically the CVD method, which is in fact a chemical vapor transfer method, which is, I think, the most established in the labs, and which has, let's say, very large monocrystalline domains. But the process conditions are extremely complex to control, and therefore it's very difficult to tune that for high volume manufacturing. And it's also very sensitive to small differences in temperature and in carrier transport. So basically, we will focus on MOCVD because we believe that this is, well, if you have the right templates, you can achieve high crystallinity. It's high volume manufacture compatible, and well, also towards time and deposition time and so on, and uniformity, it's really something that is well established. Well, this is, but in view of time, I will skip some of these slides. This is just to grow some, we started basically to work 6 years ago on ALD methods. And well, we could achieve relatively, well, we could understand relatively well our process, which has a lot to do, well, we needed to go to a plasma enhanced ALD to tune the oxidation level of the tungsten. Well, we are trying to grow tungsten disulfide, and in the reactor that we were using was a 200 degree to 450 degrees direct RF plasma reactor. We managed to grow relatively good quality material with some understanding, but there, well, basically we were limited by the reactor conditions and by the let's say the methodology on itself to a grain size of 200 nanometer. And this is basically yielding a material quality, well, a mobility of less than 1. And so this is not something that is useful for CMOS applications. So, but nevertheless, it allows us to have a workhorse in the line and doing the first integration cycles on 300 millimeters. So the first damascene contacts were made with this material, and well, it was yielding electrical, transistor signature. So the material was definitely semiconducting and integrated. CVT is the workhorse, but well, this is explaining how it works, and you see, well, I will not read the full text, but it's extremely sensitive to the processing conditions. And basically, this is something we disregard because we don't believe that this can be really easily tuned towards a stable 300 millimeter process. Nevertheless, I think most of the high-level results that are achieved today in the labs are mainly delivered through this method, and it's also very versatile, so you can very easily make very different 2D materials through this method. Well, this is the, I think, a reference paper for everybody who is growing these 2D materials, as it was like kind of breakthrough, as they demonstrate 30 centimeter square per volt per second mobility directly grow on silicon oxide for moly disulfide with a remarkably high yield. There is only one drawback in this paper. It's that the growth time was very, very long. and not completely compatible with high volume manufacturing processes. And the other thing also is that while you have non-oriented crystals, because you're growing on silicon oxide, so nothing is organizing this. And therefore, well, it has some limitations towards really boosting the performance to higher levels there. But Imec, based on that paper and so on, we choose also to work on an MOCVD reactor. So we refurbished one of the old EPI reactors we had in-house, and we, let's say, redesigned the whole reactor to make it compatible to TMDC MOCVD, and to make sure that we could work with these solid state precursors. The big advantage, well, this was one of the first wafers that came out, so you can immediately see that it's a very uniform deposition if you have the right conditions. So this is a 300 millimeter wafer. The drawback that we have is if we are working on silicon oxide, well, we cannot orient the grains. This is something that you can see here. But if you start to work on templates and so on, we can see that we can improve the orientation of the grains. And this is then when we are working on sapphire. This is a transferred TM image of 1 micron. And basically what you see is that the bottom layer, okay, we are suffering from second layer growth and third layer growth, but the bottom layer is fully organized except for 60 degrees twist angles. So basically, this is suggesting that indeed the whole layer is organized and has a certain direction. And this opens, of course, the door towards growing a full single crystalline layer on top of such templates. So we believe that now these things are engineering problems, and basically for graphene, you can basically also achieve that if you make a single crystalline template. For example, in this case, it's copper 111, but we did it for platinum 1112. There is a window to have oriented growth. And if you have oriented growth, you can close, and these layers can really like forming almost fully mono single crystalline graphene at wafer level. So the growth, towards the growth, we think that there are enough opportunities to grow the single crystalline material. It's just a matter of time and engineering. But the next thing is the transfer and mainly the control of interfaces. And well, because I was invited by Peter, I wanted to refer to this paper on the hot pickup technique, where basically they are showing that it's extremely important the way you are manipulating the flakes, and well, you need to control the strain that you build up in the flake. You need to control the flake interface between the different flakes. There is a lot of knowledge there, even when you are doing flake manipulation, and you can only make high performance devices if you have the full control of all what's happening at these interfaces. And of course, this is the mirror that we need to try to well, keep in mind when we are trying to translate things to large area. So how will we try to avoid that we build in strain? How will we try to avoid that we have, let's say, dirt or uncontrolled deposition at interfaces, because all these things will have effect on the performance of our devices. Because basically, towards mobility, towards VT shift, towards contact resistance, all these parameters have an enormous importance, and that's why I would like to address a little bit. So, well, for graphene, it's kind of common that, well, you can only have, let's say, really high performing graphene if you try to avoid all these kind of striations and so on. And this is reflected in the full width half maximum of the 2D peak. And we have a relatively good understanding that if we can really control and lower down during our manipulation, the full width half max of the 2D peak that we can go to high performant material. We also have the problem of electrohole puddles, which is also an effect of defects and well, local non-uniformities. What you can see in this is that, for example, the effect of graphene of the substrate on the graphene transfer. So these are all flakes that are transferred with a lot of care on top of one of these substrates, and you can see that if you have a very rough surface, that basically the full width half max goes up. So it means that you have all these local strain variations that are impacting this is well, basically the device performance. This is for graphene flakes, and this is then people try to do the same for synthetic materials to wet transfer, and there you can see immediately that basically it tops above the full width half maximum of 30, compared to where for flakes you can do down to 20, which is, of course, let's say, in a lot of the PowerPoint visions when we are speaking about 2D materials, well, we are drawing it like that. So we draw a square for the 2D material. You have the high K and the other high K or whatever. So you encapsulate it, but in reality, it's much more complex, and we try to schematically show here which are the fundamental factors that are all playing a role towards the mobility. So you have local strain variations, you have, let's say, non-uniform dipoles in the dielectric, you have screening in the channel, you have dipoles that are not oriented in the same way over the 2D material. And it even becomes more complex if you have an asymmetric high K, if you have one compared to the other. So there is a lot of limitations if you try to put one monolayer of material in between two three-dimensional materials. And I think this is one of the key challenges to understand how we can improve that and how we can control that at wafer scale level. I think at flake level, it's quite well understand. We go to HBN or another 2D material, we sandwich, and then a lot of these effects are gone. And then we can show the performance that is targeted. But here it's just like some measurements where you see band gap variation, differences between valence band and conduction band, just due to strain variations and non-uniformities in MOS2 flake on top of silicon oxide. So one of the questions are sums at the interface a possible solution? And so are we going in that direction? So we did quite some modeling to try to understand if sums could offer a solution there. But basically, sums themselves, they're also already having an impact, and they're changing the band gap basically of the 2D material. Just like if you heterostack 2D material on top of other, let's say molybdenum disulfide on top of other 2D material, we also see that this has an effect on the band gap. Another thing that we see we have a charge transfer that is coming from the SAMs, and basically it's not a uniform charge transfer, so it gives a kind of local charge density variations, which will also affect basically what is happening there in the 2D material, and it's not an ideal situation. Nevertheless, well, we are still looking into to try to find out. The next step that we need to understand to upscale is assuming that we grow on an epitaxial flat surface and that we have, let's say, a very high quality close to single crystalline material. How will we transfer that layer without building in plenty of strain and all kind of uncontrolled interface defects and so on? So therefore, at Imec, we developed what we called a rigid-based vacuum transfer. Rigid, why rigid? Because we think that this is a way to control at least the strain during the transfer. So we are using a glass carrier, and well, we are peeling off then. Well, we are with an adhesive and a laser release layer. We are mechanically debonding the 2D material from the growth wafer, and then we are doing a bonding step in vacuum. The bonding step in vacuum is, oops, it's 045. I will have to shorten to control basically the interface. And then we are doing a laser release. And the reason we are doing a laser release is because we are not inducing any force on the 2D material while removing that rigid carrier. So basically, it's again to try to control the strain in that whole sequence. And then you can just in a wet clean, you can remove the whole adhesive layer. And this has been demonstrated at Imec. I will go very quickly over it. These are the different steps. And this is the laser release step. And basically, this yields in a kind of transfer where, well, this is a microscope image, but the quality of the layer looks very similar to the quality on the directly grown wafer. What you also can see is that, well, the photoluminescence peak position gives also an idea about the strain, and there is indeed some strain buildup during the whole transfer. But the good thing is that it's mitigated in that adhesive layer, and when you're removing the adhesive layer, basically you can release and come back to strain levels that are almost at the same level than than before you start. So basically, this is kind of promising. What we also see and learn is that depending on which substrate you're transferring, you're seeing that there is another way of strain buildup in the layer. And this is also something that we still need to further investigate to better understand. The good news was that basically when we do the transfer, we just make very simple devices on top of the directly grown layer, the blue one, and we compare that to the transferred layer. Well, we see that basically we even gain some performance of the material after transfer. Okay, and we can do that also. Well, this is kind of similar sequence where we are doing that for graphene, because it's more difficult to release mechanically the graphene from the copper substrate. Well, here we are etching away the copper substrate, but nevertheless, it proves that you can use the same method for graphene. Okay, gate dielectric scale. Well, the transfer layer typically releases some, well, and there is always a polymer residue that remains on top, and this has an impact on the EOT that you can achieve in these devices. And so it needs to be removed. And therefore, we developed hydrogen remote plasma clean, which is a very soft clean, but nevertheless, it can still, let's say, induce quite some defectivity in your material. Well, we understand pretty well the mechanism, how it's working. We did some DFT calculation, and basically it's really the amount of hydrogen. You need to reduce as much as possible the amount of hydrogen at the surface, because if you have too much hydrogen at the surface, well, it's inducing sulfur vacancies. And therefore, it's even working slightly better at higher temperature compared to lower temperature, because you have more hydrogen adhesion at the interface. But it's pretty efficient, and but we still are suffering from some etching effects at grain boundaries. But we are still refining this method, and well, we think that we have something there. And then the next big challenge is the let's say the growth of the encapsulation step, is the growth of the of the ALD or the high K on top of your dielectric. And there basically you can do 3 strategies. Well, you can add a sacrificial 2D layer that you will functionalize. You will change the properties of that layer, and then you will use that as a seed layer. We have demonstrated that for graphene by oxidizing it and then growing a layer like that. So we could easily close the layer in 4 nanometer, and this was a record at that moment in time. So on graphene, with just a graphene layer in 4, we have a closed layer of aluminum oxide, because this is the starting condition typically. The other thing is we play with the physisorption, so with the temperature of the ALD process and with the length of the soak, so that you can have a kind of surface to start the ALD process. And then finally, what you could also do is evaporating a very thin layer of silicon or aluminum. And then on top of that, that will oxidize, bring that to there, and then you can continue over there. I will skip this part in view of time. The final problem that I would like to just briefly touch with you is the problem of adhesion, and mainly of intercalation effects that we see. So if your surface is hydrophilic and you put well, your 2D material in any kind of aqueous ambient, what you will have is that water will intercalate very fast at the surface. If you have only like a monolayer there, it can induce a kind of scrolling up mechanism, and you will find these kind of scrolled graphene here. And it's the way around, it's also working if you have a hydrophobic surface and you put the graphene on top and you put it in a solvent, well, you can have exactly the same mechanism. And this is something that we saw a lot for us, and especially for high quality material, is that as soon as we are bringing in any kind of solvent, we have a scrolling up mechanism that is happening here. And well, this is also, it's not fully reflected in this, but what you see here is 300 millimeter wafers where a 2D material has been grown or has been transferred. And as function of the growth or of the top layer or of the stack that is grown on top, we see that we can very different adhesion behavior. And this is always a concern. And it can really pop up in every step, that the van der Waals bond can really change the whole behavior. And if you want to do CMP steps and building a back end of line structures on top, there is a lot of temperature stress and integration stress that these wafers are seeing. And it's really a problematic thing to understand what is really driving these adhesion and mechanisms and so on. So again, interface control will be very key, and we need to substantially improve that. So just to conclude, well, we looked into different options, and we defined a little bit a roadmap for ourselves on how to bring these 2D materials in the pilot line. We have the first demonstrators out there, but there are still fundamental breakthroughs that are needed to really make it compatible with the semiconductor standards. And I think one of the biggest challenges is the control of the interfaces. And the big question is, can we do it with a monolayer, or will we need to have multi-layer of materials even at wafer level? This is still debatable. I think one of the big step forwards is that zero force 300 millimeter transfer. And finally, well, I just in the last slide, I demonstrate that we have an integration module ready, and well, we can start to do these things and look into yield statistics and let's say process maturity of 2D materials in 300 millimeter processing. And I think this concludes my talk.
Now it's possible to clap. All right, that didn't do that. Okay, how do I? Okay. All right. Thank you very much, Cedric. That was very impressive. And thank you also for sharing your views on the challenges and the stuff that hasn't been solved yet. That's in the true spirit of Copenhagen. We don't just want to hear the commercial, we also want to learn something. So thanks a lot for that. And I could see there was a lot of exciting discussions going on in the chat. You missed that, but now there's a chance for people from the audience to ask Cedric questions. The way we are going to do it is that you write question in the chat, like the word question and the name, right? Question, Anna, something like that. And then I will say, Anna, you can ask a question. Okay, so we'll do that. I think we will spend maybe 5-7 minutes on that. So please, if you would like to ask Cedric a question, please write that in the chat, and I will tell you to unmute your microphone. Like this question. Peter in the chat means that I have a question, right? So if you want to ask Cedric a question, you can do that with your microphone. Just and there's a question here from Miguel, and the presentation. I have to discuss it with Cedric, but we'd already discussed that at least most of the presentation will be made available. We maybe have to edit stuff out due to coming publications and things like that. There's a little bit of stuff there, but I don't know what you think, Cedric. But I will send the presentation to Cedric, and he will tell me what can be made available. Does that sound?
I just want to go through it to verify a few things, but
of course.
Yeah.
All right. So there's a question from Stein. Please unmute your microphone.
Oh, yeah. Thanks, Cedric. It was very nice. A very nice overview. You have been talking about the different 2D materials and different growth solutions and the transfer. So how do you see the universality of the final technology in a fab? Will one machine be able to handle different 2D materials, for example?
Well, I think there are several parts of your question. I think towards growth, we will most probably, well, I don't know, but it seems like we will make a difference between growing graphene and HBN type of materials and TMDC materials. But I think towards TMDCs, you can grow, if you have the precursors, you can grow them in a similar kind of reactor. I must say one thing that when we started our reactor, it's a difficult thing. It's much more difficult than initially than thought by us. We were very optimistic that we would be very that very fast we would be generating a lot of material, but it's much more difficult than foreseen. Nevertheless, we managed to have step by step a lot of these problems under control, and I think, well, it shows a quite good versatility. Towards transfer, I think a part of the transfer, the idea of having that rigid carrier is universal. Well, we also looked already into making heterostacks with this method. This seems to be doable too. There is a big challenge, and this is the delamination of the material from the growth template. And I think I can explain relatively easily. The better the quality of the material, the more the correlation you have between the template and the 2D material that is grown on top. And because you have a very good correlation, you have a very good quality of the material, but it also means that it's very difficult to peel off. If the material is less good correlated to the bottom material, well, very it's much more easy to peel it off. And there we still struggling with a very systematic and always reproducible method. And it's also a little bit different for graphene than for TMDCs. So most probably for that part of the transfer, so just the delamination part, we will have to look into several options. But there we have ideas, and I think also Peter is doing very nice work with the roll-to-roll transfer and so on. So there is towards playing with polymers and so on. There is quite some room there. But then the rest of the transfer can again be copy pasted. So I think you will need in some parts different tools, but not in all the tools.
Thanks, Cedric. That was a great answer. Are there any other questions? I should just say thanks a lot to Stephen for fighting hard to keep up with all the questions in the chat. So he did some really nice work. So part of the credit belongs to him. But there's still possibility to ask 1 or 2 questions more for Cedric before we close the session. Oh, Elias, please unmute your microphone and ask a question.
Hi everyone, and thank you, Cedric, for such a nice presentation. I would like you to, I asked Stephen about, your adhesion evaluation, and he briefly commented on a couple of methods such as full probe bending and delamination methods. So I was wondering if you can comment further on how you evaluate the adhesion of these 2D materials, especially on 3D substrates. Thank you.
That's a very good question, and I would like to have a better, or let's say less labor-intensive method than well, crack propagation and so on. We are in-house thinking about how we could do that better, and at least having faster results on how to measure this adhesion. But it's not an easy thing. And honestly, if in the literature, if in the field, somebody can think about a fast method to measure quantitatively the adhesion of a 2D material, this would be really extremely helpful in the full developments that we are doing. I don't think we have a simple method ready out there. We have some ideas to play with EFM tips and structures and so on, but all these things needs to be demonstrated, needs to be assessed if they are reproducible, if the numbers that you get from these things, if it's like stable enough, if the error bar is too high and so on. So it's a lot of work to do there. And well, if there are ideas in the field, please share it with us, because we can really use that. It's one of the weak points.
Thank you very much.
Okay, so we have 2 questions more, and then we will close the session. The first question is from Gius. Gius, please unmute your microphone.
Hey, so I was wondering if you could comment something on process window of hydrogen plasma cleaning.
Yeah, well, there is, in the initial phase, we were not really understanding our results, and then we had to go to ab initio modeling to go deeper into the results. And well, it should be as gentle as possible, but still you need to have relatively higher temperature, because the temperature prevents that you have too much hydrogen that sticks to the 2D material. But it should be very gentle, because otherwise you etch. And the etching of the polymer residue is extremely fast. So the problem that we have now is more in finding the tool that can really ignite very fast, having a stable plasma for the shortest possible time. And well, we don't have all the tools that we would like to have, but let's say that's where we are focusing on. So it's really, it's a difficult thing because the tools are not fully optimized for that. But this, we believe, can be engineered. The other thing that I would like to mention here is that most probably, well, there is still quite some work that we could do. So it's healing post-cleaning. For example, even if you have some sulfur vacancies, you could think about doing an anneal in a sulfur-rich environment, or trying with some molecules or whatever to have a healing step. In the literature, you see that quite some people are working on that. So I'm confident that if we can have a little amount of defects in there, that we will also be able to heal, or it's even maybe an opportunity to do a controlled doping of the material also. So it's most probably something we would like to play with on the longer term also.
Okay, thanks.
Right, and we have a last question from Petri. Petri, please unmute your microphone.
Hi, everyone. First of all, thank you for the presentation, Cedric. But I had a question about the remote hydrogen plasma cleaning, or relating to that. So you mentioned that you've been using this to clean the adhesive from the 2D materials. However, your colleague in the chat mentioned that this doesn't really work for graphene yet. So what have you been actually using with graphene?
I think this is a question that Stephen can better answer than myself, because for most of the graphene transfer, we are not using the TBM that we're using for, well, we're using a different polymer. And I think that for graphene, the polymer can be cleaned by just wet clean with an anneal afterwards. So we don't need to go to hydrogen exposure, because it's another polymer on top. But Steven, correct me if I'm wrong there.
No, that's correct.
Thank you very much, and thank everybody. So now I will do an experiment. Please hang on for a second, because I'm going to unmute all of your microphones. And then I suggest that we all try to clap our hands just to see what happens if we do that. That's something I really would like to try. So I'm unmuting everybody, and then we give Cedric a round of applause.
From this big group that I'm talking about, essentially every superconductive.
Thank you, Peter, as well.
Have its own.
All right. Okay. So this is it. Thank you very much for participating. I appreciate all the nice questions, and see you on Thursday, where Frank Coppens will speak about something entirely different but extremely interesting. So this is it. I will close the meeting for now, and I will ask you, when you get the feedback sheet, please fill it out, because we really like to know how to make this even better. And the other thing is that we will also send you a link to at least part of the presentation after Cedric have had a chance to look through it and edit it. All right, so goodbye, and thank you for staying with us until now. Bye-bye.
Bye, and thank you.
Bye.